Okay, welcome back, guys. We're going to be covering 8A, and there's actually only one section in Chapter 8 that we cover. Okay, and so this is going to deal with how we describe growth. Okay, it can be either growth or decay. So think about growing taller, since you were born, or let's see, what's something that decays? I don't know, the mass of a tree in the forest as it's rotting. Okay. Well, the mass, I guess, technically doesn't decay, but the tree itself is being broken up and is decaying in a sense. So what's interesting about this section is that we'll discern, or we'll learn, the difference between linear growth versus exponential growth. Okay, so most people here or think about processes that are increasing or decreasing. They think that they're doing so in a linear fashion, and that just means for every set interval of time they either increase or decrease by the same amount. Okay, so like let's say every year you get a $1,000 raise. That's $1,000 every single year. Now we'll contrast this with something that grows exponentially. And that's something that actually grows not by a fixed amount, but by a percentage. So for example, think of a cost of living raise. So let's say each year you get a 3% cost of living raise. So that first year you get 3% of what you're already making. So your salary goes up. And then that next year you get 3% of your new salary. So that increase the next year is larger than the increase the previous year. Okay? And so we'll go ahead and define these two processes. Now this can be, I know that the notes here say growth, but we'll also see some examples of decay, so things that decrease. Linear growth occurs when a quantity grows by the same absolute amount in each unit of time. Okay? So think about saving, for example. Let's say you save $50, you're able to save $50 a week. And so every week you deposit $50 over and over and over. Okay? Now, exponential growth occurs when a quantity grows by the same relative amount. In other words, it grows by the same percentage. Okay? So think about that cost of living raise, 3% every year. Well, that means that because your salary will be increasing, 3% of that increasing salary will be a larger increase every single year. All right. So here's a graphic that shows you the difference in how things increase depending on whether they're increasing linearly or exponentially. So we've got this straight town grows by the same absolute amount each year. Okay, so I'm going to zoom in here. So this line right here, guys, represents straight town. So you can see, I don't know by how much it's growing. It looks like that it starts out at 10,000, and then after 10 years right here it's gone to, I don't know, close to 14,000. So maybe it's growing by 4,000 people each year, 4,000 or 5,000 each year. Well, when that happens, if you graph it, the next year or the next 10 years it will have grown by 4,000 or 5,000 people. The next 10 years by 4,000 or 5,000 people, and then the next decade by another 4,000 or 5,000 people. And graphically what this produces is a straight line. Okay? So linear growth or decay can be modeled by a line, a straight line, where the horizontal axis represents time and the vertical axis represents the growth or decay in whatever it is that you're considering. Now let's look at Power Town. They say Power Town, guys, because when an exponent is referred to as a power, okay? And so when something is growing exponentially, it's like it's growing by power. So what happens is, well, first of all, you notice it starts off about the same, for the first 5 or 6 years, but after that, Power Town really starts to increase in population. And the reason is because it's increasing by 100% in this case. It's doubling, okay? Each year, it's increasing by a certain percentage. I don't know exactly what that percentage is, but after, it looks like about 14 years, its population has doubled. It's gone from 10,000 to 20,000. And then after, let's see, from 14 years to, that's about 28, so another 14 years, it's doubled again. Okay, but it's doubled from the previous amount, so 20,000 now becomes 40,000, etc. Okay, so that population is growing by a certain percentage. So as you keep taking a percentage of a quantity that's larger and larger, then that growth is larger and larger and larger. And so graphically, that means that you have not a straight line in which the slope is constant, but a line in which the slope is getting higher and higher. Or in other words, this exponential curve in which it gets steeper and steeper and steeper. And we've talked about this when we were talking about investments that earn compound interest. They behave this way. Okay. Simple interest can be modeled using a straight line. So you can see the difference. Compounding can be so powerful. All right, well, we're going to look at some examples. I've got several of you for you here. And we're going to do by hand so you can really see what's happening step by step. Okay. So we'll do 2 or 3 of these examples. I'll probably do this section in a couple of videos as well. All right, so it says in each of the following situations, state whether the growth or decay is linear or exponential. Sorry about that, guys. Computer died. Yeah, so linear or exponential. And then answer the associated question. Okay, so let's look at part A. The number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 750 4 years ago, what is it going to be today? Well, you may think, well, this seems like an easy question. You just say 50 plus 50 plus 50 plus 50 4 times, right? Okay, and that's true. And add that to the initial population. You get your answer, okay? But what I want to point out is that because it's increasing by 50 every single year, this is an example of linear growth, okay? And what I've got is this chart, and we're going to see what happens to the population year by year, so you can really get a sense of this idea of linearity. So I'm going to call this time, and this over here will be the final population, okay? And in here we'll do our calculations, okay? So at, let's see, well, should I start this? Well, let me start this at time 0, okay? So at time 0, there's nothing to do. The population starts off at 750. But after that first year, the population grows by 50. So you have the original population plus 50, and that gives us 800. Okay, and then over year 2, the new population, which is 800, grows by the same fixed amount, which is 50. So now we have 850. And you just repeat this process. So for year 3, we're measuring time in years. The new population is 850 plus another 50 gives us 900. And then after, let's say, 4 years, guys, it would be 900 plus 50, and that is equal to 950. So this will be your answer. This is the population after 4 years. Okay. Now here in a minute, if I can remember, I'm going to write out a formula for us, because we don't want to have to fill out a table like this and do 4 of these calculations, because what if it had asked us, what's the population going to be in 20 years? Okay, so you can derive a formula. You just take the growth rate, which is 50, multiply it by 20, the number of years, add it to the original population, and that'll give you the final population. Okay. All right. You know what? Let me go ahead and write the formula down here for you. So the final quantity, because remember, we'll be talking about different quantities, populations or prices or things of that nature. So I'm not going to use final price because that's too specific to this problem. So the final quantity for linear growth will be equal to the initial quantity. I'm just going to put initial. Now I may just well, no, I'll keep the final quantity there. So initial plus the growth rate times the number of years, or the number of units of times, unit of time. It's not always years. It could be like, excuse me, the interval of time could be like a month or a day, okay, or every 2 years. Actually, let me change that to time. Okay. And by the way, guys, I'm going to put a plus and a minus here. So this will work for decay as well. So if you have a process that's growing linearly, then to find the final amount, you take whatever the initial amount is and you add to it the growth rate, so how much is it growing per year, times the number of years, and that'll equal the final quantity. Now, if it's a process of decay, you take the initial amount and you subtract whatever this number becomes, the rate of decay. So like if it's decaying or decreasing by 50 per year, then it would be 50 times and then the number of years. Okay, so this is an equation right here that'll work for both linear linear growth and decay. All right, well, let's look at another one then. This next one's an example of exponential growth. And it's growth because it says the price of milk has been rising 3% per year. Okay, it's exponential, guys, because of the percent. It's not increasing or rising by a fixed amount, rather a percentage, a relative percentage. Okay, so this is exponential. And we'll be able to derive a formula for this as well. All right, well, I'm going to do this one the same way. We'll start with the year. This will be for our calculations. And then over here, this will be the price after each of these years. Okay. So this is So if the price of a gallon of milk, it starts out at $4, what's it going to be in 4 years? Okay, so I'll start at year 0 again. Okay, so at year 0, that's the starting year. It's starting at $4. Okay, but after that first year, what happens is the price increases by 3%. So you have to find 3% of $4. And if you remember how to do that, you've got to convert 3% to a decimal and multiply it by 4, and I believe that will give you 12 cents, 0.12. Okay. Now to find the final price, you add the initial price to it. Well, it was initially $4 plus the amount by which it grew, 12 cents, and that gives us an ending or a total price at the end of the first year of $4.12. So it's increased by 12 cents. Okay. Now you're going to do that repeatedly. So now over year 2, the new price is $4.12. So we need to find 3% of $4.12. Okay. So again, convert 3% to a decimal. I'm going to do this in my calculator. 0.03 times $4.12. And you want to round these to the nearest cent. So this is really closer to 12 cents again. But you can see it is actually more than 12 cents. So it has grown a little bit more than it did the first year. But I'm still going to call it 12 cents. Okay. So the original amount from the previous year was $4.12. And it's going to increase by another 12 cents. And that's going to make it $4.24 at the end of year 2. So what you'll notice, like in the very beginning of both linear and exponential processes, initially they look kind of the same. You don't see much difference in their growth. It's as time continues that you really start to see that bifurcation in the two. All right, so what about year 3? Well, the same thing. We need to find 3% of our new price, which is $4.24, and I'm going to use the calculator again. I'm going to hit second enter, and that will allow me to just change the price. So 3% of $4.24, and if I round this to the nearest cent, it will actually round up to 13 cents. Okay, so again, the original price from the previous year plus the 13 cents. So you can see it's grown a little more, hasn't it? And this will give us a total of $4.37. Okay. And then finally for year 4, the same thing, guys. 3% of the new price. Let's see what this gives us. I'm going to do second enter again, and I'm just going to change that 24 cents to 37 cents. And I get, now this is 13 cents and a little bit extra. Okay, so it has increased even more. But it's still closer to about 13 cents. And so the final price after 4 years is going to be $4.50. And so that's your answer. Okay? But again, like I said previously, you wouldn't want to, what if it said, what's the price going to be in 20 years? You don't want to have to keep taking 3% of the new price and adding that to the old price 20 times. So we can derive a formula, okay, and I'll do it below. Similar to the other one, so the final amount will be equal to the initial amount plus or minus, depending on whether it's growth or decay, I'll just put growth. You know what? Let me do that a little bit differently. Let me put growth slash decay rate. Okay. So it's going to be a percentage. Oh, wait a minute. No, this isn't quite right. It's the initial amount times 1 plus or minus. And what you may notice here is that this formula looks a lot similar to that formula that we use to calculate investments earning compound interest. So see, the initial used to be like our principal times 1 plus or minus the rate, or the APR. In this case, it's just going to be the growth or decay rate. Okay. So this will be a percentage that you'll have to put in there. But you'll have to convert it to a decimal. In fact, let me write that. Okay. And then we're not going to multiply it by time. We're going to raise it to the power of time. Okay. So I use that little symbol there. So the difference here is that we're not multiplying this by time. We're raising it to the power of time. So time becomes the exponent, and that's why this is referred to as exponential growth. Okay. So this is the formula that we could have used. And I'll demonstrate this to you real quick. So the initial amount was $4 times 1 plus the growth rate was 3%, which as a decimal will be that. Actually, let me write this lower. 0.03. And then I'm going to raise this to the power of time, and we were talking about 4 years. Okay. So let's see what we get using this formula. See if we get the same thing that we got from the table. So 4 times 1 plus 0.03, close those parentheses, and raise this to the 4th power. And look, we get $4.50 rounded to the nearest cent. Okay. So we get the same thing, don't we? I should have done that for the last one as well. Let me rewrite this formula here for the okay, so for the linear, final is equal to the initial, okay, plus or minus. I'm going to write growth slash decay like I did in the last one. Growth slash decay rate times time. Okay. And so if we were going to check this, where could I do it? I'm not good. Okay. Let me zoom in. Zoom in, and I think that I can fit it right here. Okay, so the final amount is going to be the initial amount, which was 750 people, plus the growth rate was 50 people per year, times 4 years, and this equals, well, 750 plus 50 times 4 is 200, and that equals 950. Okay, so I'll put a check mark right there. So guys, once you know those formulas, you can just start using those. I just like doing these tables because it gives you a real sense, allows you to grasp intuitively what's happening here, how these processes are operating. I think maybe we'll do one more. Part C, and then we'll stop for part 1. So this says tax law allows you to depreciate the value of your equipment by $200 per year. So if you purchased the equipment 3 years ago for $1,000, what is its depreciated value today? In other words, what's its value going to be today? Sorry about that, guys. My computer keeps freezing. Alright, well, this is linear decay. And it's decay because the value is depreciating. So that means going down, and it's going down by a fixed amount. Okay? So I'm going to put in here linear decay. I'll do this in the same way. And then this will be the final price. Okay. Or, well, not, let me use the word value, the final value of the equipment. Okay. So at year 0, nothing's happened. The equipment is worth $1,000. After year 1, you get to depreciate it by $200. Okay, so subtract $200, and now its value is $800. And then after year 2, its current value, which is $800, depreciates $200 more, leaving you with the current value of $600. And then we repeat this process for that 3rd year, and it would just be $600 less $200. And so its final value, after 3 years worth of depreciation, is going to be $400. Okay. Now, if I had used that formula from above, the final amount, or the final value, would be equal to the initial value. And we're going to use a minus because this is a process of decay. The rate of the decay, well, it's $200 per year times the number of years, so 3. Well, 200 times 3 is 600. And 1,000 minus 600 is 400. Okay, so I put a little check mark there. Alright, guys. And I've gone almost a half an hour, so I think that's a good stopping point for this first video. And then we'll finish. We've got 2 more examples. We'll do them both by tables, and we'll use the formulas as well. And then we'll finish up the rest of this section. Alright, so I'll see you there in part 2.